Welcome to my session about what the CRaC, coordinated restore checkpoint on the Java virtual machine. And yes, I have to thank you that this conference is in person again. It's so good to be in person. I hope you also all enjoy that. First of all, who struggles from slow JVM startup here? Someone? No one? One. Yay. Okay. So just curious what it is, right? Okay. First of all, about me. My name is Gerrit Grunwald. I'm working for Azul Systems as a developer advocate. Did a lot of JavaFX in the past, now doing more stuff on the back end and with the JVM. And at Azul, we do JVMs and Java. That's what we do. Okay. If you would like to have the slides, you can find them here. So you might take a picture. I tried it. Even if it's transparent, it should work. Otherwise, you can look at SlideShare and just look for Han Solo, which is me, and then you will find what the CRaC slides there. And if you are not able to do it now, just come to me after my session. All right, so Java is great. We have a vibrant community, as we can see with conferences like this. We have hundreds of Java user groups. We have thousands of free open source software projects. But the real star of the whole environment is the Java virtual machine. It doesn't matter which language you use, as long as it runs on the JVM, that's cool, right? The question is, how does it work? And I bet all of you know better than me, but let's have a short look into how the JVM really works, and just a part of it, because it's quite complex. So we start with a Java file, your source code, you store it. Then this will go into the Java-C compiler, and it will spit out a class file. This contains cross-platform bytecode. So that means you have a JVM, doesn't matter on which platform, as long as it's in bytecode format, you can run it on that platform using the JVM. So once we have the class files, the question is, how does it get into the JVM itself, right? Therefore, we have the so-called class loaders. Here it looks quite simple, but even the class loaders are quite complex. But we don't want to talk about class loading here. So the class loaders take care about getting the class file into the JVM memory. And from JVM memory, it gets into the so-called execution engine, which is the thing I would like to explain a little bit more in detail, but really just a little bit. And you can already see this contains, it's not only the execution engine, it contains multiple parts. And these parts are the interpreter, the C1 JIT compiler, formerly known as the client compiler. Who remembers client compiler? Nobody? Really? Okay. Oh, one. And then there's the C2 JIT compiler. That is the formerly known server compiler. And then there's a profiler and a garbage collector. But we only talk about these three things because that's important for the CRaC project. Okay. So it works as follows. The interpreter takes the code line by line, interprets it into the CPU instruction set, and the JVM is watching it and profiling. And it is in literally method counting. So that means if a method was called, let's say, 5,000 times, then the JVM, there's a specific threshold, and it says, okay, we called this method so often, we take it, put it into the C1 compiler, right? The C1 compiler, I already told you, is the formerly known client compiler. The reason for that is this came with JDK 7, and in JDK 8 it was the default that we have both compilers in the JVM. Before JDK 7, you can choose between the server and the client compiler. And the reason for that is, if you have, for example, a desktop application like IntelliJ or Eclipse or NetBeans, which is a Java application running on the desktop, you double-click the icon, and it should just appear, right? You don't want to wait until the compiler starts. Yay, have to compile it, optimize it. 10 seconds later, whoa, there's a window. This thing, the C1 compiler, is really fast, doesn't do a lot of optimizations. The reason for that is to reduce startup time, right? This is the main reason. So the JVM takes the code, the hot code from the interpreter, and puts it into the C1 compiler, and this one compiles it and makes it available as compiled code as fast as possible. And then again, the JVM is watching that code. And again, it starts to count how often this code was called. And then there is another threshold. If this is reached, then the JVM says, well, wait a minute, we take that code and put it into the C2 compiler, because the C2 compiler is much more complex. and can optimize the code to produce really performant, fast code, but it takes longer, okay? So this is called tiered compilation because we have this multiple compilers there and also an interpreter. And between these different stages, we have execution levels. And you see we have 4 of them, or 5, if we include the 0 one. And the 0 is interpreted code. Then we have 3 levels for the C1 compiler. The reason for that is, again, if you run something on desktop, you might want to profile the code to find problems or stuff like that. So you run it in level 3. But at the moment where you have the high optimized code, there's no need to run it in level 3 again, so you can run it in level 1, which is faster, right? And then there's level 4, which is the C2 compiled code. Usually what's used, or what is the preferred way of using is, we have the interpreted code level 0, then it gets into level 3, C1 compiled code, including profile information, and then this profile information will be used in the C2 compiler to further optimize the code. That's the preferred way of doing it. You don't have to remember that it's just the information on the side. And then this leads me to the so-called execution cycle. This is in principle the same that I told you with all these nice graphs, just a little bit more formal. We have the interpretation phase in the beginning, which is slow. We profile that, counting methods. Then we put the code into C1 compiler, and then it will be compiled very fast without optimizations. Then we have, again, a profiling phase that tries to figure out if this code was called often or more often, and then it gets into C2, which produces the highly optimized code. So this is usually how it works. And then we have this little thing over there that we would like to try to avoid, which is called de-optimization. Who knows what it is? Yes, 1, 2, maybe 2. So this is definitely a performance hit, and I come to that in a second. So de-optimization is if we take a block of code like this, right? It's a very simple if-then clause. We just check if a value is larger than 0 or greater than 0. If this is true, the result should be 3. And if not, the result should be 0. And then we print it. So this is our code. Now we figure out with the profiler that 99% of the time, it's always greater than 0. So that means the result is almost always 3. The compiler does the following. It takes the whole block here and it reduces it to this. And it guards the value in the JVM. So that means if I pass in a value equals 5, this is true, result is 3, that's it, fast. Now, in case the result is 0, which can happen, then suddenly the compiled and optimized code is not valid anymore. So that means the JVM takes the code, this one, and throws it away, right? And then it has to reinterpret and recompile the whole block again with both types, with both paths. And that's de-optimization. You can imagine, once you're in this state, the code is already fast, and suddenly you have a case like this, and then the JVM has to redo the interpretation, C1, C2 compile for this code. It's a performance hit because interpretation is slow, right? So this is de-optimization. You would like to avoid that if possible. But it happens. It can also be a benefit later on. Let's say the code changes, or not the code, let's say the behavior of the application. Then the JIT compiler is able to optimize the code by doing a de-optimization and optimize it for the new situation, right? So this is quite beneficial also. Okay, that's all great, right? But it takes time, right? Interpretation, C1, C2, profiling, and so on. And that leads me to JVM startup. And this is, I came up with this chart last week after thinking about it for a long time because it's not so easy. If we talk about JVM startup, then what we usually mean is the JVM and or application until the first response. This is what's generally, if people speak about JVM startup, it's these 2 blocks. Because if you just take a JVM with one class, hello world, start it up, it's blazingly fast because nothing to do, right? It's just the JVM itself, and then it's one class. And there's nothing to optimize. The real problem happens if you load your own application, you have dependencies, all the classes have to be loaded, resources have to be initialized, and so on. That takes a lot of time. This including the JVM startup, is what people define as JVM startup. So there is no general way of saying the JVM is always slow, because it's not the case. It depends on your application. And then there's another one which is called JVM warmup. That means if you have an application, the first time it responds, fine. Now you trigger it more and more and more. Then you will see sometimes it gets faster and faster and faster. The reason is your code will be touched by using it. It will be further optimized, so caches will be warmed up and so on. And this is then the JVM warm-up. So just keep in mind when people talk about that, you really have to think about what are they talking about. Is it JVM startup? Is it JVM warm-up? Does it include the application startup and all these things? These days, you find a lot of people just blaming Java for being slow on microservices. It really depends how you define that, right? Okay. If we take a look at the JVM performance graph that we just created some time ago, we see here 3 different colors, which is yellow, just low, the down left corner here. And this is the interpretation phase. And you see, it's not really long, right? It doesn't take that long, and it's really just a short time where we interpret code. Then it went into the green phase, which is the C1 compiler and profiling. And then it gets into the C2 compiler, and then we see it ramps up with the performance because it's doing all the optimizations and stuff. So this is the JVM startup, if I just define it in this chart. And then we have things like this reoccurring gaps here in the end. This is usually garbage collection, because where we have the stop the world, okay, JVM stops, cleans up the heap and all that, and then continues running. So this is these gaps. And then here in the beginning, this is the optimizations. You see these big gaps here where the code was already fast and suddenly it drops down because there was another branch, for example, that was hit by the code, and then it has to re-optimize, or first de-optimize and then do the optimization again. So that's all cool. If we take that to a microservice environment, then it means first time we run the stuff, we have JVM startup time, right? Second time, again. Third time, again. That sucks, because it really takes time. Always we start up a service, we have to wait for it until it's really at high performance level, right? Wouldn't it be great if we can do something like this? We start it up once, and then the next time we start it, it's directly fast, and so on. That would be the ideal world. So let's take a look at possible solutions to improve startup time here. First of all, there's class data sharing, or shortly named CDS. Who knows what CDS is? Someone ever heard of it? One? Yeah, because it's not really well known. It seems like it's per default on since JDK 12. So you might already use it if you over JDK 12. And there is app and dynamic CDS. And what it does, it dumps internal class representations into a file. So that means when you load the classes, the class loader doesn't have to collect everything from everywhere, but it's already preloaded in a specific file and can directly take it from there. You might think, well, yeah, is it really that big of an improvement? And yes, it is, because these files can be shared on each JVM startup. So every time you start up the JVM, it doesn't have to load the classes from everywhere, but directly from this file. You can further, how is the word? I don't know, modify it, that's it, or tune it. And there is no optimization or hotspot detection here because this all happens at class loading time. This is before it even gets into the interpreter. And it can speed up your loading times to 1 to 2 seconds. And there is a nice blog post from Ionit Balozin, who's also here. And he explains it, and he also has a session at several conferences about CDS and how to tune it to make the startup faster. So if you don't use it, you probably want to check that out. So you will find it in the slides. And it happens here, right? So you have the class file, and then it goes, there is the CDS where it works. And after the JVM memory, then we have interpretation C1, C2 compile, and so on. Okay, so it doesn't really help us with this compiling phase, which takes some time. Then there is ahead of time compilation, which probably everyone heard about. And then my typical question is, who's using GraalVM native image in production here? Someone. No one. Okay? And there's a reason for that, right? But we don't want to dig into this. So if you use AOT, then you don't have to interpret bytecodes. And there's no analysis of hotspots if you just do plain AOT. You don't have to compile code at runtime. This is all done before the code is running, right? You start at full speed straight away, which is great. It's a native executable, and GraalVM native image does that. So problem solved, right? Well, not so fast, because AOT by definition is static. So that means the code is compiled before it is run, and that means the compiler has no knowledge of how the code will actually run later on. There are ways to improve that, which is called profile-guided optimization. And in case of GraalVM, what they do is they also have a JIT. So they run the code once with a JIT and do a profile, and then they use this profile and apply it when they create the native image. So with this, you can reach higher performance in the end. And if we take again a look at the JVM performance graph, then usually, and this is really, you can't really, there's no general rule, but usually you will get up to 60% of the performance of the JIT just by using plain AOT compiled code. But that can vary, of course. It really depends on the application. And once you use PGO, then you can even reach higher levels, like up to 90% of the JIT. But still, this is fixed code. There's no way to optimize it at runtime anymore, right? So this is really once and forever, where the JIT can always do PGO. It's like an ongoing PGO. This is what the JIT does. And to do that, of course, you need to profile first, to create the profile to be, and I think it's not part of the GraalVM Community Edition, if I'm right. I think it's only in the Enterprise Edition, so it's not for free. Okay, so if we do a short comparison between AOT and JIT, then AOT can use limited use of method inlining, for example, because it can only do that in the profiling phase, but not at runtime, where the JIT can do that all the time with all code that is running. And there's no runtime bytecode generation in the AOT, where JIT has, of course, can create bytecode at runtime. Reflection is hard in at least GraalVM. It is possible and it gets better, but it's still, it's not really as simple as it is in the JIT. And you can't really use speculative optimizations. These are optimizations that will be done at runtime. So that means the JVM is watching the code, profiling it, and figures out, oh, wait a minute, this branch is called very often, so I optimize the code for this branch at runtime, where the JIT can do that, where AOT can't really, right? So only in the profiling phase, you can do one shot, and then it's optimized for this one. But if it changes at runtime, there's no way to further optimize. And the overall performance typically will be a little bit lower using AOT compared to the JIT. But the biggest disadvantage that I see is that the deployed environment when IoT native image is completely different from the development environment. So people came to me after another session about that and told me, you know, we have the problem, I run the code and I run all the tests and all the tests have been green. I used the native image in production and it crashed. How to debug that? Native code is not JITted code, it's different. And this conversion into native code leads to sometimes to strange effects that are hard to debug. This is really the biggest drawback that I see here. On the other hand, native image starts with full speed from the start. It's directly fast, where the JVM or the JIT needs more time to start up. Then we don't have an overhead at compile time or at runtime because there's nothing to compile. It's already compiled, where the JIT does the compilation at runtime, right? And the memory footprint, of course, is smaller because in AOT, you only compile the code that you need. But you also need to know all the code that is available. That means all the dependency, all the classes that are used later on in your application need to be known to create a native image. Where the JIT, no problem, right? You can even load stuff during runtime. It will then optimize it at runtime. Okay, so that means the JIT disadvantage is mainly it requires more time to start up, and we have a CPU overhead to compile the code at runtime, and we have a larger memory footprint, okay? So let's take a look at a different approach here. There is a project called CRaC. Does someone ever heard about that? It's a Linux project. It means checkpoint restore and user space. It's already part of the kernel since 2013, so it's not really a new thing. And it was made to freeze a running container application, then save or checkpoint the state of this container application to disk, and later on just restore it from the disk back into memory. That's the idea. And if you still don't know what it means, then if you have a laptop and you just keep it running and you close the lid, then the operating system will figure out, oh, the lid was closed. It saves all its state to the disk. The next time you open it up, it loads it from disk and it's back there. That's exactly the same thing. Creating a checkpoint, or let's say a snapshot, and then if you restore it, it just takes the stuff from the disk and puts it back into memory and keep it running. That's checkpoint restore. It's already used by OpenVZ, by Linux containers, Docker, and Podman. They may make use of CRaC on Linux systems, so that you might have even used it without knowing it. And it's mainly implemented in user space, not directly in the kernel. And the main goal was the migration of containers for microservices, right? And it relies on this proc file system. That means even on Linux, not all Linux distributions use proc, right? So if it's not used, you can't use CRaC there. And it can checkpoint a lot of things like processes and threads, application memory, memory map files, shared memory, open files, pipes and FIFO sockets, inter-process communication channels, timers and signals, and it can restore or rebuild a TCP connection from one side only. No handshaking involved, which is quite interesting here. All right. It also has some challenges, of course, otherwise it would be too easy, right? So first of all, if you create a snapshot on one machine or a checkpoint, you can imagine it's not that easy to take that on a different machine and restart it. Because you might have open files that are not available on the other machine. There might be settings in the operating system. There might be a different architecture like ARM64 or x64. All these things, not easy to do that, okay? Starting multiple instances of the same application on one machine, also not a good idea because it won't work. Because the PIT, the process ID on Linux, which is unique, will also be part of the snapshot, and that means you restore it. The first time will work. The second time, if the PIT is already taken, Linux will say, no, sorry, I can't run it again, right? There are solutions for that, and we are also working on a solution to fix this problem. And you are right if you guess, oh, wait a minute, if this PIT is already taken by any other process, it won't run. That's correct, right? And this happens. So, using that on a Java virtual machine, you should think, oh, this is just an application running on Linux, so I can just checkpoint it and restore it, right? Yes, if it's just the JVM, this would probably work, but the problem is in the JVM, you run your own application, and your application has files open, it has connections to a database or whatever, and if we just checkpoint the JVM and store it, then the next time you restore, your application think, okay, I'm connected to the database, and nah, you are not, right? Because it's done, because you shut down the JVM by doing the checkpoint. So this is not so easy to do that. And for that reason, we created CRaC, which is a great name. It's coordinated restore at checkpoint, and the biggest part here is the coordinated. So I told you the problems that you can run into, and the coordination here means we try to fix some of them, at least. So first of all, CRaC comes with a specific version of CRaC that we patched, comes with the JDK. That means it's always, we make sure that you have the right version of CRaC that will be used. And the heap is cleaned and compacted. This is in principle the same process that will be used if you do garbage collection, right? So we clean and compact the heap, so the JVM is in a safe state. The CRaC project can throw checkpoint exceptions in case you forget that there was an open file, then it will fail and it will give you an exception and tell you, here in this class you forgot to close a resource. And it comes with a pretty simple API. We will take a look at that shortly. And it creates checkpoints using either code or JCommand. So you can choose if you would like to do it in code or if you would like to use JCommand to create the checkpoint. And because sometimes people ask, oh, okay, I have a multi-threaded application, so now you create a checkpoint. How can you make sure that everything is really step down and not really a problem with multi-threading. Well, this is quite easy because we use the JVM save point mechanism. This is exactly the same thing that is used for garbage collection. And garbage collection also works, right? So the JVM is the master of the whole process thing going on in itself. So it can just stop everything and restart it. So that's not really a big deal. Okay, so the whole thing is an OpenJDK project. So that means it's not, we are working on that and we created it, but we passed it to the OpenJDK project to hopefully make it available in the future for everyone. That's based on OpenJDK. It's led by one of our engineers, Anton Kozlov. So if you would like to know more about it, you can find it at this URL. And now to give you an idea of what we need to do to make the application aware of checkpointing and restoring it, it's you have the running application. Before we create the checkpoint, there must be some mechanism to let your application know you will be checkpointed right now, right? So, and that's what we do. And the same thing when you restore it, then again, we have to let the application know you got restored from a checkpoint. So if you need some resources, do something, right? This is the main idea why we need an API. And we have 2 points to, when you start it, we have 2 parameters, which is -XX colon CRaC checkpoint 2 equals path. And this path means we just pass this parameter to the JVM, and in case there's a checkpoint, the JVM knows where to store the checkpoint. That's the main idea. It's just a folder, you define it, and then the JVM knows once there's a checkpoint triggered, I will store the checkpoint in this path. And if you would like to restore it, you just call Java -XX colon CRaC restore from and point it to the path, right? So this is the main thing that we added in terms of the command line parameters to make it happen. And the API, so that means the stuff that you are working with, is in principle just one interface. It's called resource. It only has 2 methods, before checkpoint and after restore. And yes, that means you have to change the code. Sounds terrible in the beginning, but you don't have to do it for all the stuff, right? So, for example, mainly it's open files, it's database connections, sockets, stuff like that. And usually you handle that in a specific class. You usually have something like a database manager or whatever. You have something that is responsible for that part of the code. In this class, you have to implement the resource interface, right? And then the CRaC project, let's say, will take care about that. So the JVM is prepared to trigger all these resources. When a checkpoint is triggered, it will call the before checkpoint, and when it will restore from a checkpoint, it will call the after restore methods in these resources. And to make that work, we have to not only implement the interface, we also have to register it somewhere in the JVM, because the JVM needs to know, okay, you have this interface, but I didn't know it. So you have to let me know that it is there, register it somewhere. And for that, we have a so-called context, right? So, and that context makes sure that first of all, you can register these resources in that context. And you can get the context if you call core.getGlobalContext. And then you can register your resource in that context. It looks like this. You have your class, you implement the interface resource, then you get the context, and then you call on the context, register this resource. That's the main idea. That's all you need to do to make sure that your resource will be triggered in case of a checkpoint. And then the context will maintain the list of all the resources, and it will also take care about the order. Because let's say you have resources that depend on each other. You might have a database. You instantiate or establish the connection to the database first, and then you have another resource that writes to the database, right? So that means database has to be there first. And with this, in the way you register the resources in this order, we keep that into account, and that means if you call before checkpoint, the context will call them in the reverse order. So that means, let's say we have the database connection first, and then we have the other resource that uses the database connection. If we create a checkpoint, first we close the resource where we use the database, and the last one will be the database, which makes sense. And if we do a restore, after restore, then we do it in the same order how you registered them to make sure everything is in the same condition as it was after startup. So that's the main idea. Okay, Here's the code that can be used to create a checkpoint, and the method name is a bit misleading. We might change that because it looks like it's checkpoint and restore. No, it's only checkpoint. And that leads to the fact that if you create a checkpoint, the JVM will be shut down. You can't do that and keep everything running because we have to close all the resources to create the checkpoint correctly. And then you don't want to re-establish them. It would be possible in theory, but at the moment, the JVM will be shut down after creating a checkpoint. So you can do that in code, or you can use J command, but I will also show you how to do that. Okay, let me give you a simple example that hopefully will explain it, how it works. So I created a very simple demo. It's just a scheduled thread. Every 5 seconds, it will call a loop. And in this loop, it will create a random number from 1 to 100,000, and the loop goes also from 1 to 100,000. And then it will check if this number is a prime number, right? And there's a method, is prime, you put the number in, and the first thing, I also have a cache. The first thing is the method will check, is the result already in the cache? Check, is it? Okay, it's in there, just return the result. This is pretty fast because it's only in memory. If it's not in there, we have to calculate the number if this is a prime number. And if you have a large number, take some time, okay? Then we have the result, we put it in the cache, and then return, which is slower, of course. Okay, this is just how that's the whole application. And to make it a little bit more realistic, the cache will forget values after 10 seconds. So that means usually if you cache something, you don't want to keep it forever, right? So that means if values are outdated, you would like to wipe them out of the cache, to keep the cache small. This is just to give you an idea, because this is how applications work. So this is just to make it a little bit more realistic. So that means the first time you run it, it will be pretty slow because every number is not in the cache, has to be calculated, and then this goes for 100,000 times. Then the second and the following runs or iterations, it should be faster and faster because the cache will be filled up, and so the results can get out very quickly out of the cache. I made some tests with that, and you see here it's just the performance level to 0, and then we have the iterations, and on another machine, it reached the optimum performance around 9 iterations, right? And then you see it goes up and down and up and down. This is because the cache will remove stuff, it will be re-added, and so on. So which is usually the behavior that you see in your applications. You won't never see a straight line. It has full performance at 1, right? It's always like going up and down. Okay, this is what we should see. And now I will do a demo where I just put it into, I hope it's readable. This should be 2 shell windows. I put it into slides and I will show it later on also in reality, but here I can explain it better. So I start the jar file with the parameter, CRaC checkpoint 2, and I point it to the CRaC-files folder. This is the folder where it should store the checkpoint. The second shell we will use in a minute. So I start it up, I put some system out print lines there in these methods to see the order I registered them. So first I registered the generic cache and then the main class. And then it took 27 seconds to fill and for the first iteration, because this machine that was taken on a virtual machine on a MacBook Pro, so it took forever. So on my MacBook Pro, the M1, it took 1 second to do it in the first run. But here it took 27, which is good because now we see the improvement. Second run, 10 seconds, and then I just skipped through it. It got faster and faster, and it was always 5 seconds between these runs, right? So, and then at one point, you see the cache. Okay, here it's 17 milliseconds. That means cache was nearly completely filled. That means all the results are in the cache, and that makes the code quite fast. That might be the point to create the checkpoint here, right? So I go on the second shell, and I can either use J command and call the CRaC jar file here with the command jdk.checkpoint. I can also use the PID. So you see there is a PID up there, 4240. I can also use J command 4240 jdk.checkpoint, is the same. I use the jar file here. So and what happens then is, you see the before checkpoint methods have been called. In the reverse order, I registered them, as I said before. Then it creates the checkpoint, and then the JVM was killed. So I'm back to the shell. So that's it. At this point, I will find the checkpoint in the CRaC-files folder, okay? So now I wait, and I wait more than 10 seconds, and this is the JVM warm-up time, right? Because in this example, because this is not really the JVM startup, because my application warmed up. I filled the cache, and then at one point it was filled up, and then it was fast. But this applies also for JVM startup, right? Okay, now I've waited longer than 10 seconds, and I'm telling you the 10 seconds because usually I told you the cache will forget values after 10 seconds. So if I restore it now, the first time I hit the cache, it should figure out, oh, wait a minute, all the values are outdated, and it should wipe out everything. And it would do that. That happened on my first run. And then I figured out, yes, the problem is if you have time-dependent data, then of course you have to keep track of that, because the checkpoint is really, it's the state when you create the checkpoint, it's saved to disk, including all the timestamps that you use somewhere. And if you rely on that, the next time you use them and compare them and see, oh, wait, they are all outdated, you have to take care about this delta, right, between the checkpoint and the restore. So what I did here was, and the code is available, it's pretty simple, because before I create the checkpoint, I just store the system epoch milliseconds in a variable, and when I restore it, I do the same. I use the epoch milliseconds and calculate the delta between the checkpoint and the restore and apply that to all values in the cache to make sure that they are still valid. So that's the way to get around this problem. So if you try it, you might stumble upon this problem. So you really have to check your code and be aware that if you have time-dependent or state-dependent data, let's say you have a buying process in your system where you have something like, okay, there is, it was already checked out, and now you have to check later. The state of this cell is maybe it's waiting. And then you create the checkpoint. The next time you restore it, you will figure out, oh, that's outdated. So you remove it. But so things like that. So if you handle time-dependent data, you have to take care about that. Okay, if I restore it now, I just call java-x CRaC restore from pointer to the folder, and then bam. It will first call the after restore, and you see it's in the same order as I registered them on top. And then it will continue running here. It's the 12th run, it's quite fast, and the cache is already filled because it took all the stuff from the saved state. Right? So that makes it really fast. Okay, and then it will continue running every 5 seconds. So for the JVM, there was no checkpoint. The JVM doesn't know. For the JVM, it's like, oh yeah, I'm keeping running for all the time. I don't care. Right? So it's really, this is like you take the JVM, put it in a black hole, and then at some point in the future, you take it out and get it running again. And the JVM has no idea that it was really stopped. Okay? So, like I said, creating the checkpoint from the command line, it's done like this. You can either use the jar or the pit, or you can use it in code. So there is a debate if it makes sense to use it in code, but you can, for example, add that line to your code at a point where you know everything is warmed up, and then you can just check if the folder that you define is already, if it contains files, you don't create the checkpoint. If it doesn't contain files, you create the checkpoint. Stuff like that is possible. The question is now, when to do the checkpoint, because it's not an easy task. It really depends. First of all, you can do something like in main, after everything was established, you can say at the end of main, you would like to create the checkpoint. It's totally valid. You could also do something like, if you know after the first response, you create the checkpoint. This is usually what you do. But you can also apply some workload to your application and say, I would like to have it in a warmed up state because I need that, right? If you, for example, have high-speed trading companies, they do something like that. They start up their servers very early in the morning, sometimes hours before the market is open, just to make sure everything is warmed up, right? And they can get around this by using CRaC, for example. So what we do to test it, there is a parameter called -XX plus print compilation. This will print out all the compilations that are happening in the compiler. That means if you start it, you will just see nothing. It's just scrolling endless. But at one point, you will see it's slower and slower. Less compilations are done. That means most of the code is compiled and optimized. that's a good point in time to create the checkpoint. Right? That's how we do it. This is, but there is no, this is just a rule of thumb. You have to play around with that. You observe the moment, if the compilations are ramped down, and then you create the checkpoint using J-command, for example. Okay. Typical usage, of course, is not to run it straight away, but to run it in a Docker container, right? So that means you run your application in a Docker container, you create a checkpoint in that container, then you save the state of that container, and the next time you start it up, you start from that saved state. And that will be really fast, okay? And some words about compatibility. At the moment, it's only available for Linux x64, and the JDK that you can download is, we build that from time to time, it's 1702. That's the only one we have. ARC64 would possibly follow in the future. There is no reason to not do it, but we have it not yet. So if you would like to test it, then you have to use Linux x64. And then upgrade. So if you have created the checkpoint on a Core i7, for example, this will run on a Core i9. But downgrading, like you create the checkpoint on a Core i9 CPU, won't work on a Core i7, because the JVM will optimize code not only on the platform itself, but also for the CPU. And if the CPU architecture offers some specific things that makes it better, then the JVM will use that. That means if you have code that was optimized for the Core i9, it won't work on the Core i7, but the way around works. But we will also work around that. So there is an idea that we have to make sure that even this will work, the downgrading. At the moment, it doesn't work. So if you create something on a, let's say, a different architecture level, same CPU, but different architecture level, then make sure that it's always not on the latest one and try to run it on an older version. That won't work. And in a Docker container, it also works on a Mac. So that means if you create a Linux container, you can run it on a Mac as long as the architecture is the same, and I will show you that in a minute. Okay, and there's one more point, because people pointed out that, yeah, but if you run it in the cloud, you never know the nodes that you get, and this is not really true, because I checked that, at least for Azure. And if you create node groups, then Azure makes sure that they always use the same CPU architecture. You can use different groups of nodes in a Kubernetes cluster, but that's up to you, right? So if you make sure you use the same architecture in your node, a group of nodes, then this will work at least on Azure. Okay, the demo code, if you're interested in that, it's available here. And I just give it to you. You can play around with that. It's an easy thing to just download the JDK, fork that project, and let it run, and it will directly work. And then you can dig into the code and play around with it, right? But it's all, like I said, the slides are also available. You will find it there too. All right, so okay. The question is, how good is it really? Because I talked about something that we created. I showed you a demo that I did, and of course it worked great because it's a demo that I did. Of course, we made also some tests with real frameworks like Spring Boot, Micronaut, Quarkus, and we did an XML transform. This is the time to first operation, and it's in milliseconds. And you see Spring Boot took around 3.9 seconds to respond. Micronaut was around 1 second, Quarkus even faster. And then the XML transform took 4.3 seconds. That was on plain OpenJDK. So now we created that with using CRaC, a checkpoint, and started from the checkpoint, and then this was the numbers. And that's quite impressive, right? So we really got down to milliseconds here, to 38, 46, 30, and 53 milliseconds, just for the starting up from using the checkpoint. And the reason why these numbers, even if these are totally different on OpenJDK, they are pretty much in the same range using CRaC. The reason here is it's just I/O we depend on. It's loading from the disk back into memory, plus if you have to restore some resources, that might take a little bit longer. But that's the reason why it's so fast. It doesn't matter if it was 4 seconds or just 1 second. In the end, the difference is not that big. But you see, you can really gain a lot of JVM startup improvement here by using CRaC. And these demos are available in this repository that I already told you. So you can, if you don't trust me, just try it on your own. So everything's there. You can just fork it, run it, and see these results on your own machine. All right, summary. CRaC is a way to pause and restore JVM-based application. It doesn't require a closed world as with native image, and it benefits potentially, it has an extremely fast time to full performance level. It eliminates the need for hotspot identification, method compiles, recompiles, and de-optimizations. Of course, that has to be done before you create the checkpoint, right? After the checkpoint, no need anymore, but I have a chart for that too. And we have improved throughput from start, and it's an OpenJDK project, and it can also save some money. So let us have a look at that. If you run something in a cloud infrastructure, you usually know that. This is the CPU utilization, and this is time. And if you spin up a JVM, then usually you see this. You see a large peak in the beginning, and then it drops, and then it levels out at some point. This is usually the JVM startup time. And this peak that we see is interpretation and compilation overhead and optimization that is going on. So if you create a checkpoint there, right, and start from there, then it eliminates this startup time overhead here and also the CPU overhead, because we don't need that anymore. And because I know that some companies, they tend to use very high power nodes in a cluster with lots of CPU cores just to reduce the startup time, to get rid of this peak, right, to make it usable. With this, you don't need. You can use low power nodes, let's say, or not so many cores, because you create the checkpoint here, and then you don't need all that power just for the startup, right? Okay, so you will find all the demos and stuff here, github.com/CRaC. There you will find the JDK you can download. We update that from time to time. And there is also then a release notes, what we added, what we changed. If you find problems or you stumble upon something, don't be afraid to file an issue or ask questions, right? This is an ongoing project. We try to make it better and better, and we hope it will become part of the JDK at some point. There's also a wiki page. It doesn't contain that many information, but you can check it out. And now, let's take a look at the real demo, because that's the interesting part. So what I do, I created a Linux container with this demo code that I showed you before on one of my older Core i7 machines, right? And now I start that container on this Mac, and you see, okay, first run, right? No checkpoint here. Takes forever, 27 seconds. Cache is empty. And it will take some time, but you see, I run that natively on my Mac, but it was created on Linux. We just have a Linux JDK, which is the beauty of Docker. You can't run that on an M1 Mac, of course, right? I had to make sure that the architecture is at least the same. And this, what I do here is, this is a Core i9 machine, and the checkpoint was created on a Core i7, so that works in that direction. The way around wouldn't work. And you see, yeah, okay, oh, now we're getting faster and faster. It really takes some time. And then at some point you will see, brrp, now, yeah. And now it will go every 5 seconds. There will also be a hit at 12, because that's the first time the cache will start wiping out stuff. Oh, even not here. Cool. Because usually it does. Whatever. So this is running now, right? Now it's warmed up. It's more or less fast. Okay. Now I just started from a checkpoint, and let's see. Oh, it's there. And another one. And you see it was directly there. It was directly at iteration 18 with 18 milliseconds. And so you can imagine, if you have to spin up your microservice multiple times at the same time, it's just there. You don't have to wait until it warms up. And that's the beauty of using CRaC. And with this, I don't know, do we have still time? I'm not sure if we might have some minutes left for questions. But with this, I'm done. So if you have any questions, then we can probably talk about that right now. So, questions? No questions. If you are too shy, you can also grab me outside. Yes?
I want to know some use cases for this software.
For this project, for example, is if you use, who knows AWS Lambdas, for example? Yeah, who uses that? Not so many, but Lambdas is something where they really suffer from the startup time because they have to spin up the JVM just to do a little bit of work, and then they close it again. It's always when you have a microservice that you start up either multiple times or you start it up and close it shortly after again. Then most of the time is spent in starting up the JVM and your application. The actual work really just takes a second and then it will shut down again. These services will definitely benefit from this kind of start because you can directly start it up from the checkpoint. That means you saw it was 18 milliseconds the first time I restarted it, and that's the benefit. It doesn't make sense if you run an application server and you would like to create a checkpoint there. It doesn't make sense at all, right? You don't want to use a checkpoint on an application server. But for microservice environments, this is pretty much very useful, especially if you scale up stuff multiple times. Yeah, another question.
The CRaC project into your build pipeline, so it is already there after you finish your build?
That's a good question. We are not sure about that. There is no really, at the moment we don't have a good workflow to integrate it into CI/CD because at some point you can imagine you have to create the checkpoint first once you can restore from there. So because this is not really ready for production yet, I think this is something we have to figure out a way to make it possible to use it in a CI/CD system. And at the moment, there is not really, you have to figure it out on your own how to make that work for you. If you create the checkpoint and then deploy it with your application, but if you change the application, means you have to change the checkpoint again, so it depends. Yes?
I think it's a follow-up on his question. So, first of all, we need to use your JDK, right?
Yeah.
And the second question, now my application, it's a Docker image. So how do you combine the Docker image with the checkpoint? So that
What I do, I pointed you to my demo project, and in the README you will find how to do that. So what you usually do, you create a Docker image, and there's a Docker file. You can directly do the same that I did. Create a Docker file, you start it up, you log into the Docker container, run the application, and create the checkpoint from another shell that you also log into, right? In principle, you do the same that I showed you with 2 shell windows, but you just have to log into the Docker container while it's running. And then you create the state, you can store it, the Docker image. You can store the state after you created the checkpoint, and then you can just restore or start this Docker container that has the checkpoint in it. That's the way to do it. And like I said, in the CRaC 4 demo, I put everything in the README, and if you follow it, you can just create it on your own machine to play around with it. Yeah. Oh yeah, I'm not sure if we have, I think we should stop here, but if you have questions, you can just come to me and I will try to answer them over there in the lobby. Okay? Thanks for attending.